Welcome to Penetration Testing, Incident Response, and Forensics, brought to you by IBM. In this series, we're focusing on forensics. In this video series, we'll be diving into what forensics are. We'll learn about the forensic process, chain of custody, and learn about using the data that we collected in data files, operating systems, applications, and network traffic. Let's get started. Welcome to What is Forensics, brought to you by IBM. In this video, we'll be covering what is digital forensics. We'll dive into what types of data that forensics deal with, and then we'll focus on the objectives and need for digital forensics in the cybersecurity industry. We'll wrap up with reviewing the steps to the forensic process. Let's get started. As always, we're going to start off with a definition of digital forensics. So digital forensics, also known as computer and network forensics, have many definitions, but generally speaking, it is considered to be the application of science to the identification, collection, examination, and analysis of data while preserving the integrity of the information and maintaining a strict chain of custody for said data. Throughout this entire series, we'll be talking about data a lot, so I think it's important we take a second to define what data really is. The first step in the forensic process, which we will cover in much greater detail, is to identify potential sources of data and acquire data from them. The most obvious and common sources of data are desktop computers, servers, network storage devices, and laptops. Now, in these, you're going to find in the environment of wherever you're conducting your forensic analysis, inside the computers or servers, you might find CDs or DVDs, internal and external drives. These could be solid-state drives, spinning disk drives. If they're external, they could be flash drives, external hard drives, things like that. There's volatile data, which means data that only exists in this snapshot of time. So if we were to disconnect from the internet or restart the computer or close an application or proc an authentication, we change the state of what's on the computer. So volatile data means it's very time sensitive and we have to capture it now because we may not always have access to it. Network activity, you can get that from the internet service provider with a court order. You can look at logs to see what network activity existed. You can get data from that. Application usage. Applications often store previous sessions or saved projects or things like that. So they contain they're rich with data. And then portable digital devices. So this is just in the environment, in the physical space. Are there cell phones? Are there audio recorders? Are there security cameras? Are there digital cameras? There are so many things that can contain data that we need to be aware that it might not all be digital or it might not all be just on the computer. We have to be aware of the surroundings as well. So all of this is the world of data. And so I know it's a very broad term. In future videos, we'll actually be breaking down how we use data from each of these sources. But for now, know this is what we mean when we say data. According to the National Institute of Standards and Technology, the most popular use case for forensics goes in criminal investigations and incident response. Anytime you look up any literature about forensics, it's usually closely tied to one of those two things. However, the practice and techniques of forensics can actually be applied to many areas. Some of those include operational troubleshooting, log monitoring, data recovery. For data recovery, there are many tools that can recover data from lost systems, whether the data was lost intentionally or not. Data acquisition, so sometimes the data is not lost, you know where it is, you just need to get to it. In the case of maybe workstations that were retired or being redistributed, maybe the employee left the company and wiped the computer and you need data back from it or just need access to it. Things like due diligence, regulatory compliance. So existing and emerging regulations require many organizations to protect sensitive information and maintain certain records for audit purposes. So regardless of the situation, there's going to be many applications for forensics. Let's dive into what the objectives of forensics are and then break down those steps. When I asked IBM resident System Information and Event Manager Raul what the objectives of digital forensics were, this is what he had to say.
Any investigation and agency or any department of a company or a police investigator will need a method to take away the required information from the digital device in a documented manner. Otherwise, it will get destroyed by any good lawyer. So, one of the main objectives is to document both the process to take the evidence and the evidence itself. Also, our next objective will be to postulate what was the motive behind if it was a crime or if it was an accident. Both identify and postulate the motive. Digital forensics also design these procedures to help everyone involved to be able to protect the evidence and protect the procedure. If there is any step on the procedure to take away the evidence that it's known, the investigator or the forensics agent will be accused of evidence tampering. So, data acquisition and duplication, depending on the countermeasures set up on the computer. If it's a computer in a criminal case, might be protected. So we need to be able to warrant that this procedure will be completely secure and the data will not be changed while we are copying it. So another objective will be to identify what is the necessary evidence as quick as possible. Processes are time sensitive and you need to be able to determine where to search for evidence. Our next objective, we have to write reports in a timely and very clearly manner for anyone to be able to understand it. We cannot write reports that will be only understood by engineers. And the last one, but it is superseded by a couple of objectives up and away, will be to preserve the evidence by documenting the chain of custody. Serving the chain of custody.
NIST breaks down the 4 steps of the forensic process into collection, examination, analysis, and reporting. We'll be breaking these down further in the next videos, but for now, as an overview, the collection is being able to identify, label, record, and acquire data from all the possible sources while preserving the integrity of the data. Examination will be the processing large amounts of the collected data to assess and extract data of particular interest. Analysis, analyzing the results of the examination using legally justifiable methods and techniques. And then finally, reporting on the results of the analysis. In the next video, we're going to work on collection and examination. We'll see you there. Welcome to the forensic process, data collection and examination, brought to you by IBM. In this video, we'll be covering what the different types of data are. We'll then go over the 3 steps of data acquisition, the role chain of custody plays in data collection, and then what obstacles are faced during examination. Let's get started. In the introduction of forensics, we went over lots of different types of data types. Things from CDs and DVDs, internal and external drives, volatile data, network activity, application usage, and portable digital devices in the physical space. But collecting data goes far beyond what we discussed there. Each collection method actually has its own unique challenges to consider. So beyond that, think of externally owned property. So maybe an incident happened and it involved an employee's personally owned computer or cell phone. Things like computers at the home office where you might not have access to them. And if they're at the home office and you can't access them, what are alternate sources of data? Is there a backup somewhere, a server that it's connecting to? Things that we have to start to think outside of the box because we no longer have access to a physical device. Things like logs. So it's really important for the conservation of data and auditing to be able to have a centralized logging system if possible. And if your organization and your legal department agree to it, even things like keyloggers, where you can monitor the keystrokes on a computer, is another way to gain data, though that is far less common in organizations. The National Institute for Standards and Technology breaks down the collection of data into 3 main categories. The first is actually developing a plan to acquire the data. Now, important factors for prioritizing what data to collect is trying to determine what the value is going to be of that data, whether it's volatile data or not. So volatile data, as we discussed in the prior video, is data that's only available now in this moment, whereas if there was a state change to the computer, if it were to shut off, disconnect from the network, something requires authentication, something could change the state of that data. That data would then take priority. How do we get the volatile data first? And then, how much effort is it actually going to take to actually get this data? So those are all things we have to consider when, making our plan on how to acquire the data. The second step is actually getting your hands on it. In this section, we'll be using our forensic tools to collect the volatile data and then duplicate the non-volatile data sources so we don't compromise the original data source. And at that point, we would need to secure the original source so that it's not tampered with in any way during the investigation. The last step that we deal with is verifying the integrity of that data. So the forensic tools that we use can create hash values for the original source. So when we take an image or a backup, it'll create a hash value for that we can then compare to the duplicated version, because if anything changes to the original, it's going to generate a different hash value, and we can see that the two are no longer identical. So using those will allow us to validate the integrity of the data. One of the most important things to be mindful of when doing data collection is observing the chain of custody. So a clearly defined chain of custody should be followed to avoid allegations of mishandling or tampering of evidence. So what it is it involves keeping a log of every single person who had physical custody of that evidence, documenting the actions they performed on it, being able to store the evidence in a secure location when it's not being used, make sure that you make a copy of it so that you're not working on the original, and then verifying the integrity of the original versus the copied evidence. So the chain of custody basically is an overview, it's an audit trail of saying, here's everything that came into contact, the who, what, when, where, and why, so that at any point in time in a court of law, you can say there are no gaps in how the evidence was handled. This is so important that we're actually going to be spending more time on the chain of custody in a separate video. But for now, know that it has to be top of mind whenever we're collecting data. The next step in the forensic process is examination. Now, examination is exactly what it sounds, examining the data that we've collected. With that, though, there are lots of obstacles that we face, and it's not going to be the same for each scenario. By and large, though, these are the common hurdles that we have to overcome. We need to bypass controls. So operating systems and applications may have data compression, encryption, or advanced access control lists, which make it very difficult to examine the data that we've collected. And not only just getting to the data, but just how much of it there actually is. So a hard drive may have hundreds of thousands of files, not all of which are relevant to the case at hand. So being able to filter through all that to find what's most relevant for our case is pretty time consuming. Luckily, though, there are tools that we can use and different techniques that exist to help filter and exclude data from searches to help expedite the examination process. Now that we've covered the collection and examination of the data, the next two steps in the forensic process are going to be the analyzing and reporting. We'll see you in the next video. Welcome to the Forensic Process Analysis and Reporting, brought to you by IBM. In this video, we'll review the considerations taken when conducting an analysis, and then we'll learn about the components that make up the forensic report. Let's get started. The analysis should include identifying people, places, items, and events, and determine how these elements are related so that a conclusion can be reached. The analysis really is putting all the pieces together. Coordination between multiple sources of data is crucial in making a complete picture of what happened during the incident. The National Institute of Standards and Technology provided an example of an intrusion detection system log linking an event to a host, the host audit logs linking the event to a specific user account, and the host intrusion detection system log indicating what actions that user performed. So we have multiple sources here, all contributing to what the analysis of the picture is. Having the most complete picture possible is what lends itself to solving these incidents. In some cases, it could even solve pretty big crimes. I'd like to share a few of the most famous crimes that were solved using digital forensics. Perhaps the most famous case to be solved through digital forensics is that of the BTK killer Dennis Rader, with BTK referring to his MO of bind, torture, kill. Rader enjoyed taunting police during his killing sprees in Wichita, Kansas. But this also proved to be his fatal flaw. A floppy disk Rader sent to the police later revealed his true identity. He was soon arrested, pled guilty, and spent the rest of his life behind bars. Another more recent case solved with digital forensics was that of Dr. Conrad Murray, personal physician to Michael Jackson. Digital forensics played a crucial role in the trial, in that after Jackson passed away unexpectedly in 2009, the autopsy found Jackson's death to be the result of prescription drugs. Investigators discovered documentation on Dr. Murray's computer showing his authorization of lethal amounts of drugs, and he was convicted of involuntary manslaughter. Another one was going to be the Craigslist killer. When one woman was killed and another attacked after meeting individuals on Craigslist, Boston was on high alert. Fortunately, law enforcement had their suspect within a week of the murder thanks to digital forensics. Investigators tracked the IP addresses from the emails used in Craigslist correspondence to an unlikely suspect, a 23-year-old medical student, Philip Markoff. Without the trail of digital evidence, who knows how prolific Markoff could have become. Now, these are just a few examples of the many, many cases that are solved by digital forensics. Let's move on to reporting. Your forensic report or case summary is meant to form the basis of your opinions. While there are a variety of laws that relate to expert reports, the general ground rules are as follows. If it's not your report, you can't testify against it. Your report needs to detail the basis of all your conclusions, and you'll need to detail every test conducted, the methods and tools used, and those results. Let's break down the different components of the forensic report, and then we'll discuss some best practices as provided by the SANS Institute. In the forensic report, there are 4 major categories: the overview case summary, the forensic acquisition and examination preparation, the findings and report, also known as your forensic analysis, and then what your conclusion is. Let's break these down a little further. The first section is going to be the overview. This section explains how the investigator originally got involved in the case and how the initial incident or request or evidence was initially provided to them. Please take into account that this document could be used in the court of law, so it must be concise and complete as possible. The next section is the forensic acquisition and exam preparation. This section is very important, as you must detail your interaction with the digital evidence and the steps taken to preserve the forensically acquired evidence. Any additional steps you take, such as forensically wiping storage, examination media, should be notated in this section of your report. This section of your report is usually where you, as the examiner or analyst, encounter the digital evidence and thoroughly document what you've done, which is really important to the integrity of the digital evidence and your chain of custody. An expert report must first detail exactly what analysis was used, how the expert conducted their examination and analysis, what tools were used, what were the results of that, the details of the machine that was tested, the machine that was used to conduct those tests, and then the conditions that the tests were conducted in. Any claim an expert makes in the report should be supported by intrinsic, reputable sources. For example, if an expert report needs to detail how domain name service works to describe a DNS poisoning attack, then there should be references to recognized authoritative works regarding the details of domain name services. For findings and report, really there's a set of best practices outlined by the SANS Institute. The first one is going to be taking lots of screenshots, bookmarking evidence via your forensic application of choice, using your built-in logging and reporting options with your forensic tool, highlighting and exporting data items into CSV or text files so that they're universally accessible, and using a digital audio recorder versus handwritten notes when necessary. That way you can avoid all confusion. To wrap up this video is going to be the conclusion of the report. In the conclusion, it's going to be a summation of all your findings and analysis. It should be concise, but also technically accurate to all the points you made throughout the report. And while it is good to summarize, it shouldn't be so long that it overshadows your actual analysis that you did, which will carry most of the weight of your finding. In the next video, we'll be covering how to use data we get from data files. We'll see you there. Welcome to Using Data Files, brought to you by IBM. In this video, we'll be learning about the different file systems. We'll learn what methods are used for gathering and preserving the integrity of files. We'll learn about what metadata from files can be useful. And then last, we'll learn what techniques forensic tools can perform for data analysis. Let's get started. According to the National Institute of Standards and Technology, a file can be many different data types, including a document, an image, a video, or an application. Successful forensic processing of computer media depends on the ability to collect, examine, and analyze the files that reside on the media. For the sake of this video, we're not going to deep dive into each of these. However, after the video is over, I highly recommend finding a good resource and learning what you can about the different file systems, their capabilities, and their limitations. For the desktops, Windows, Unix, and macOS, these are the major file systems that exist. There are many more, especially in the Linux-Unix world. While it may seem easy to get data from files such as a document, a spreadsheet, an audio file, a video file, what's more intangible is the files that are no longer there, whether that's deleted files, slack space, or free space. For deleted files, when a file is deleted, it's not typically erased from the media, in this case, let's say, a hard drive. Instead, the information on the directory's data structure that points to the location of the file is marked as deleted, so it gives the appearance of no longer being there. However, the file is still on the hard drive. It just has the appearance of being gone. What happens to that is that when you start saving other files and you use up the space on your drive, it overwrites anything that has a deleted directory. So until a hard drive is completely full, there is definitely ways to recover files that have been deleted. Now, slack space has to do with minimum file size allocation. So depending on the file type, the operating system will have a minimum file size saying, I'm going to at least dedicate this much space for this kind of file. Even if the file itself is smaller than that allocated space, that wiggle room between is known as slack space, and data can be recovered from it. The last one is going to be free space. Free space is the area on the media that is not allocated to any partition. That free space, though, may still contain pieces of data from the deleted files. So we delete the files and it appears we have free space. But really we know that until that free space is taken up, it's still recoverable. Another type of information we can get from files is the MAC data. No, I'm not talking about Apple's Macintosh. I'm talking about modification time, access time, and creation time. This is all metadata that's captured when a file is interacted with. So it's important to know as much information about relevant files as possible. So recording the modification, access, and creation times allows analysts to help establish a timeline of the incident. Modification time is the last time that file was changed. So not just opened, but if anything got altered or modified and then resaved, that is a modification. Access time is going to be the last time that it was actually opened. And then creation time, when the actual file was established or created. So between that, modification, access, and creation, analysts can depict a pretty good timeline of what happened in that file's history. So now we ask ourselves, how do we get a hold of this data? How do we collect it? Now, there are two major camps in collecting files. There's the logical backups, and then there's taking a bit-by-bit image. So for a backup, it copies the directories and files of a logical volume. It does not capture other data that may be present on the media, such as deleted files or residual data stored in slack space. Think of this as if you were just plugging in an external hard drive and making a copy of the backups, right? Or if you use an automatic backup system that periodically will re-back up all the files within your file system, either when there's a change or at a predetermined time interval, that's a logical backup. One of the benefits of a logical backup is that it can be used on a live system if using the standard backup software. Usually that software backs up when either there's a change or at a standard time interval, so it's easy to be done on a live system and be confident that you're getting those changes. However, it can be resource intensive, both time and resources of the computer. Now for imaging, this generates a bit-for-bit copy of the original media, including free space and slack space. Bitstream images require more storage space and might take longer to perform than logical backups. If evidence is needed for legal or HR reasons, a full bitstream image should be taken and all analysis done on the duplicate. More often than not, we are going to be taking an image. And what that means is it's really just a snapshot of saying this is exactly what was on the computer at this moment in time. You just freeze time, create a clone of it, and you're able to interact with that clone. Now, you can do that disk to disk, meaning I can export, I can, for instance, take a Mac, put it in target disk mode, which essentially turns the whole computer to an external hard drive, and then just clone over everything that's on it onto another computer so that it's ready to be interacted with. Or I can do disk to file. So I can say, take a clone of this and create a file that I can then, put on an external media and transport around as necessary. Imaging should not be done on a live system since data is always changing. If done on a live system, you no longer have an accurate timestamp of what's happening because all the volatile data is continuing to change over time, so a logical backup would make more sense. Now that we've discussed the different type of data you can get from files, as well as how to collect it, I want to spend some time to talk about the techniques that we use as facilitated by forensics tools. Many forensic products allow the analyst to perform a wide range of processes to analyze files and applications, as well as collecting files, reading disk images, and extracting data from the files themselves. The first technique that tools help facilitate is just using file viewers. So instead of using the original source of applications, you can use a single tool to review every type of file, which expedites the searches and eliminates the need for a working native app for every file type. The next one is going to be to uncompress files. So, zipped or compressed files are pretty common, but pretty early on in the forensic process, the analyst should be uncompressing files so that those are included in the searches. The only real caveat to that is sometimes things called compression bombs, things set up by the hacker or the malicious person that essentially is sometimes tens, hundreds, thousands of files compressed within each other, but staying up to date on your antivirus or event detection should really help mitigate that. Another one is using a graphical user interface for displaying directory structures. This practice makes it easier and faster for analysts to gather general information about the contents of media, such as the type of software installed, and likely the technical aptitude of the user who created the data. Most products can display Windows, Linux, and Unix directories, and others are specific for macOS. Another key technique is identifying known files. So it may seem a bit obvious, but it's very beneficial to eliminate unimportant files, such as known good operating system and application files from consideration. Analysts should validate hash sets, such as those created by NIST's software reference library project or personally created hash sets. Again, this helps simplify the process and helps you focus on the files that you need. The big thing here that a lot of the forensic tools do is performing string searches and pattern searches. So a string search is aid in pursuing large amounts of data to find keywords or strings. Various searching tools are available that can use Boolean, fuzzy logic, synonyms and concepts, stemming, and other search methods. The last one really is accessing file metadata, which could provide us a lot of context about the file and potentially information about the author. So we're not going to go into all the individual tools in this video, but again, after this video is over, there's going to be some extracurricular activities where I encourage you to go out and review a lot of the forensic analysis tools that exist. Welcome to Using Data Operating Systems, brought to you by IBM. In this video, we'll learn about the different volatile and non-volatile data in operating systems. We'll learn about the different operating systems that exist today and learn about what log information may be useful to forensic analysts. Let's get started. The National Institute of Standards and Technology explains that operating system data exists in both non-volatile and volatile states. Non-volatile data refers to data that persists even after a computer is powered down, such as a file system stored on a hard drive. Volatile data refers to data on a live system that is lost after a computer is powered down, such as current network connections to and from the system. Some examples of volatile data are slack space, free space, network configuration connections, any running processes, any files that are opened at the time, the login sessions, and the operating system time. All of these dependent on being in the current session of a live system. Examples of non-volatile data would be the configuration files, any logs, application files, data files, swap and dump files, any hibernation files, or temp files that exist on the system. These will be there regardless if the system is rebooted or not. We always want to start with collecting the volatile data because we don't know how much longer we'll have access to it. To my right, we have listed here a prioritized list of the things we should be grabbing from most important to I'll get it when I can. The first thing is going to be all the networked connections. So this will change if a computer changes power states, and you might not get that information back. Most operating systems, Windows, Linux, and macOS, and all variations of, will have ways to list what network connections they have on there. Login sessions, contents of memory, any open and running processes and open files, which should be pretty easy to get, though some third-party applications, some forensic tools, do make it easier to capture that whole process. The network configuration itself, and then what the operating system time is going to be. Now, in this particular video, we're not going over all the tools themselves, but we will be reviewing them before the final quiz. Let's move on to non-volatile data. For collecting non-volatile data, one of the things that we have an option for is shutting down the computer if needed. The things you have to consider are what your options are. Normally, it really boils down to two different methods. One is a natural shutdown, usually with a power button or a command within the operating system. The other is, in the case of portable devices such as laptops, cell phones, things like that, is removing the battery. The problem with hard shutdowns like that, same goes for like desktops, if you just pull the plug out of the wall, is if they have spinning hard disks or if they're in the process of reading and writing data, that data can become corrupted if not shut down properly. So something to really keep in mind because the integrity of the data is always at the forefront of every forensic expert's mind. Next, we'll be collecting the actual file system data, which is pretty straightforward. It can be done with thumb drives, external hard drives. You can take an image if you need. We did talk about in the video we made about collecting data from files, whether to use standard backups or imaging. For file system data, that's really, it can go either way. The users and groups listed will be a part of the operating system where you can get that data, as well as the password hashes, or if they just have a document with a list of their passwords, go for it. Shared networks, so every system has the ability to reach out to other systems with permission, and so you can see what devices were networked to this system. Which should allow you to gather some information, and then logs. So every operating system has a native logging feature. There are many applications that forensic analysts use that can help facilitate collecting those logs as well. For collecting non-volatile data, one of the things that we have an option for is shutting down the computer if needed. The things you have to consider are what your options are. Normally, it really boils down to two different methods. One is a natural shutdown, usually with a power button or a command within the operating system. The other is, in the case of portable devices such as laptops, cell phones, things like that, is removing the battery. The problem with hard shutdowns like that, same goes for like desktops. If you just pull the plug out of the wall, is if they have spinning hard disks, or if they're in the process of reading and writing data, that data can become corrupted if not shut down properly. So something to really keep in mind, because the integrity of the data is always at the forefront of every forensic expert's mind. Next, we'll be collecting the actual file system data, which is pretty straightforward. It can be done with thumb drives, external hard drives. You can take an image if you need. We did talk about in the video we made about collecting data from files, whether to use standard backups or imaging. For file system data, that's really, it can go either way. The users and groups listed will be a part of the operating system where you can get that data, as well as the password hashes, or if they just have a document with a list of their passwords, go for it. Shared networks, so every system has the ability to reach out to other systems with permission, and so you can see what devices were networked to this system, which should allow you to gather some information, and then logs. So every operating system has a native logging feature. There are many applications that forensic analysts use that can help facilitate collecting those logs as well. And on the topic of logs, let's spend a minute to look at the different scenarios in which you might want to collect different log files. The type of logs you should be collecting will largely be dependent on the incident that's under analysis. In this case, we have examples of in case of a network incident, in cases of unauthorized access, or in the case of a Trojan virus or worm attack. In case of a network hack, you're going to want to collect the logs of all the network devices laying in the root of the hacked device and the perimeter router, the one provided by the internet service provider. The firewall rule base may also be required in this case. For unauthorized access, you'll want to save the web server logs, application server logs, the application logs themselves, the router or switch logs, firewall logs, database logs, and the intrusion detection system logs, etc., depending on what forensic tools or detection systems you're working with. And lastly, in the case of a Trojan virus or worm attack, you'll want to save the antivirus logs apart from the actual event logs pertaining to the antivirus. When I asked System Information and Event Manager at IBM, Raul, what his thoughts were on the different operating systems, this is what he had to say. Windows is a widely used OS designed by Microsoft. The file systems used by Windows include FAT, exFAT, NTFS, and REFS. Investigators can search out evidence by analyzing the following important location for Windows: the recycling bin, the registry, the thumbs database, files, browser history, and print spooling. For macOS, he mentioned that macOS is a Unix-based operating system that contains a Mach 3 microkernel and a free BSD-based subsystem. Its user interface is Apple-like, whereas the underlying architecture is very Unix-like. He also had a best practice that macOS offers a novel technique to create a forensic duplicate. So to do so, you can put the perpetrator's computer into target disk mode. Using this mode, the forensic examiner creates a forensic duplicate of the hard disk with the help of a FireWire cable connection between the two PCs. Essentially, if you reboot a Mac holding the letter T, it boots it into essentially an external hard drive that, when plugged into another system, can just be duplicated. For Linux, he said that it's an open source, Unix-like, and elegantly designed operating system that is compatible with personal computers, supercomputers, servers, mobile devices, networks, and laptops. Unlike the other operating systems, Linux holds many file systems of the ext family, including 2, 3, and 4. Linux can provide an empirical evidence if the Linux embedded machine is recovered from a crime scene. In this case, forensic investigators should analyze the following folders and directories. The system32 config file. This contains system configuration directory that holds separate configuration files for each application. The var log is a directory that contains application and security logs. They're kept for about 4 to 5 weeks. The home user folder, this directory holds all the user data and configuration information. And last, the password directory, which has the user account information in it. So this concludes the data that we can gather from operating systems. Up next is application data. We'll see you there.
Welcome to Using Data Applications, brought to you by IBM. In this video, we will learn about the different components of an application and how they are meaningful to a forensic analyst. We will also learn about the different types of applications that provide meaningful forensic data and what considerations are taken when collecting application data. The National Institute of Standards and Technology summarizes application data as the following. OSs, files, and networks are all needed to support applications. OSs to run the applications, networks to send application data between systems, and files to store application data, configuration settings, and logs. From a forensic perspective, applications bring together files, OSs, and networks. Let's start by breaking down the components of an application that matter the most to forensic analysts. The first component are the configuration settings. Configuration settings may be temporary or set dynamically during a particular application session or permanent. Many applications have some settings that apply to all users and also support some user-specific settings. The settings may be stored in the following three ways: configuration files, runtime options, or added to the source code. A configuration file is usually a text file or a file with proprietary binary format. It may or may not be stored on the same host as the application. Runtime options are applications permitting certain configuration settings to be specified at runtime through the use of command line. Some applications that make source code available, like open source applications or scripts, actually place user or administrator specified configuration settings directly into the source code. Next, we look at the authentication of an application. Applications may have external authentication, where the authentication takes place on a directory server, for example, in which case the external authentication would have more information than the host. Proprietary authentication is most commonly seen in usernames and passwords that are application, not OS specific. Pass-through authentication is where the application uses whatever the OS authentication is. Lastly, a host user environment is seen mostly in enterprise environments where authentication is checked for an application against a domain of approved users. Most applications generate some type of logs and record them to an OS-specific log or something proprietary. The most common types of logs are event, audit, error, installation, and debugging logs. Event logs record actions that were performed, the date and time each action occurred, and the result of each action. Audit logs or security logs specifically track audited activities such as authentication attempts. Error logs track errors applications have with timestamps. Installation logs track when an application is installed or updated, and the debugging logs are usually only meaningful to the software developer. Data is a very broad term, but nearly every application is specifically designed to handle data in one or more ways, such as creating, displaying, transmitting, receiving, or modifying data, as well as protecting and storing data. Application data files may be generic or proprietary in file format and may be stored in multiple different places such as databases, temporary files either in memory or applications, or permanent files. It should be noted that temporary files may be created due to improper shutdown of an application, and those files may be located within an application or at an OS-specific location. Supporting files may offer the least amount of critical information out of all the components, but when all else fails, it can provide bits of information that may lead to a better understanding of the data. Many applications come installed with supporting documentation or user manuals that can help analysts determine what any given application was used for, and where the application may store the supporting files. Links or shortcuts, as many Windows users know them as, are pointers to something else. Analysts can determine what program a link runs and where it is located. Graphics usually are of little interest, but if an icon image are recovered, analysts can sometimes determine which executables were running. Application architecture tells us how an application logically separates the components, which in turn gives analysts a better idea on where the application data will be stored. Applications are built to function as local, peer-to-peer, client-server based, or a combination of the three. Local applications are meant to keep everything local to the host. There are applications like text or graphics editors and office productivity suites. Client-server structures are the most complicated because they can have anywhere from 2 to 4 locations of data between the local host, application server, and database server. Web-based applications substitute local hosts for web browser and add a web server. Peer-to-peer applications are set up to directly share information between hosts, such as file sharing, instant messaging, or chat applications. Certain types of applications are more likely to be the focus of forensic analysis, including email, web usage, interactive messaging, file sharing, document usage, security applications, and data concealment tools. Let's deep dive into a few of these to provide examples, starting with email. Email has become one of the most predominant means for people to communicate electronically. A single email hosts an incredible amount of seen and unseen data. On the surface of an email message, we have a header which usually details who the message is being sent to and the body of the email that contains the content. Hidden away in the header information is data such as the type of email client the sender used, which mail server sent the message, as well as the importance of the message and if there is specific content type, such as attachments or embedded graphics. From end to end, information regarding a single email message may be recorded in several places: the sender system, each email server that handles the message, the recipient's system, as well as antivirus, spam, and content filtering services. Next, we have web usage, which breaks down into data we can gather from the host and the web server. Web data we can get from the host typically lies in the web browser application. Analysts can get favorite websites, history of sites visited with timestamps, cached web data files, and any cookies that were saved. On the other hand, we have the web servers, which typically keep logs of the requests they receive. These logs will give us timestamps of each request, IP addresses, which web browser made the request, what the type of the request was, and the resource requested. Web data provides a rich amount of meaningful data, even when data is not accessible from the host. The last type of application I want to cover is interactive communications. This includes group chats, instant messaging, and audio-video applications. Group chat typically uses a client-server architecture. The most popular standard group chat protocol for simple text-based communication is Internet Relay Chat, or IRC. Instant messaging application configuration settings may contain user information, lists of users that the user has communicated with, file transfer information, and archived messages or chat sessions. And lastly, with the typically progressing integration of audio and video technologies, such as voice over IP, people are permitted to conduct telephone conversations over networks such as the Internet, providing more media-based data. With the overview of application data, the last portion of this video will discuss the collection of this data. This should be a review of content we've covered in prior lessons, so this will be a high-level overview. Application-related data may be located within file systems, volatile OS data, and network traffic. Volatile OS data may contain information about network connections used by applications, the application processes running on a system, and the command line arguments used for each process, and the files held open by applications, as well as other types of supporting information. Given the nature of volatile data, these should be considered first. The most relevant network traffic data involves user connections to a remote application and communications between application components on different systems. Other network traffic records might also provide supporting information, such as network connections for remote printing from an application, and DNS lookups by the application client or other components to resolve application components' domain names to IP addresses.
Welcome to Using Data Network Traffic, brought to you by IBM. In this video, we'll be reviewing the TCP/IP basics and how it relates to forensics. We'll also learn about the different sources of network traffic and how to examine and analyze it. Let's get started. The National Institute of Standards and Technology says that analysts can use data from network traffic to reconstruct and analyze network-based attacks and inappropriate network usage, as well as to troubleshoot various types of operational problems. The term network traffic refers to the computer network communications that are carried over wired or wireless networks between hosts. As we begin this video series into gathering network data, it's important to have an understanding of TCP/IP and its meaning in forensics. The application layer enables applications to transfer data between an application server and a client. The most common examples are HTTP, DNS, FTP, SMTP. These are all things we've heard before, but these are ways that application servers can communicate out. Next is going to be the transport layer. And most common when we talk about the transport layer, we think of packets. So it's responsible for packaging data that can be transmitted between the hosts. The two most common protocols used in the transport layer are TCP, the Transmission Control Protocol, and UDP, the User Datagram Protocol. In each case, the packets will contain a source and destination port number, which is useful for forensic analysts. The IP layer, also known as the network layer, routes packets across networks. It's the fundamental network layer protocol for TCP/IP. Other commonly used protocols at the network layer are ICMP, the Internet Control Message Protocol, and the Internet Group Message Protocol, the IGMP. ICMP is a connectionless protocol that makes no attempt to guarantee that its error or status messages are delivered because it's not designed to transfer application data. It doesn't have ports. Instead, it has message types which indicate the purpose of each ICMP message. For example, the ICMP message type destination unreachable has several possible message codes that indicate exactly what was unreachable: network, host, protocol, etc. IP addresses are also often used through a layer of indirection. This is most commonly done through DNS or domain name services. So when people need to access a resource on a network, such as a web server or email server, like a website, they typically just type in the website's name, like www.nist.gov, rather than that server's IP address. One, it's a lot easier to remember nist.gov, but also IP addresses can change. The server name won't. And last, we have the hardware layer, also known as the data link layer. This layer handles communications on the physical network components. The best known data link layer protocol is the Ethernet. To tie this all together, I'd like to quote the article from the National Institute of Standards and Technology, that each of the four layers of the TCP/IP protocol suite contains important information. The hardware layer provides information about the physical components, while other layers describe the logical aspects. For instance, events within a network, an analyst can map an IP address, which is from the IP layer, to the MAC address of a particular NIC, which is a physical identifier at a physical layer, thereby identifying a host of interest. The combination of the IP protocol number, which is the IP layer field, and the port numbers, transport layer fields, can tell an analyst which application was most likely being used or targeted. We rely on all of the layers. When analysts begin to examine data, they typically have limited information, most likely an IP address of interest and perhaps protocol and port information. But now that we've covered the layers of network data, let's go into the main sources of network data and break those down. The first source I'd like to talk about are firewalls and routers. Network-based devices such as firewalls and routers, and host-based devices such as personal firewalls, examine network traffic and permit or deny it on a set of rules. Firewalls and routers are usually configured to log basic information for most or all denied connection attempts and connectionless packets. Some log every single packet. Network-based firewalls and routers that perform network address translation, or NAT, may contain additional valuable information or data regarding network traffic. Some firewalls also act as proxies, and in addition to providing NAT and proxying services, firewalls and routers may perform other functions such as intrusion detection and VPN. Next up are packet sniffers, which are designed to monitor network traffic on wired or wireless networks and capture packets. Normally, a network interface controller, or a NIC, accepts only incoming packets that are specifically intended for it, but when the NIC is put into promiscuous mode, it accepts all incoming packets that it sees, regardless of their intended designations. Most packet sniffers are also protocol analyzers, which means that they can reassemble streams from individual packets and decode communications that use any of the hundreds or thousands of different protocols. Intrusion detection systems, or IDS, is something that we have covered in previous videos. IDSs perform packet sniffing and analyze network traffic to identify suspicious activity and record relevant information. Remote access servers are devices such as VPN gateways and modem servers that facilitate connections between the networks. This often involves external systems connecting to internal systems through a remote access server, but could also include internal systems connecting to external or internal systems. In addition to remote access servers, organizations typically use multiple applications that are specifically designed to provide remote access to a particular host's operating system. And although most remote access related logging occurs on the remote access server or the application server, in some cases, the client also logs that information, so we should look for that as well. Security Event Management Software, or SEM, is capable of importing security event information from various network traffic related security event data sources. Think IDS logs, firewall logs, and it correlates those among all the different sources. It generally works by receiving copies of logs from all the different data sources over secure channels, putting them into a standard format, and then identifying related events by matching IP addresses, timestamps, and other characteristics. Network Forensic Analyst tools, or NFAT, typically provide the same functionality as packet sniffers, protocol analyzers, and SEM software into a single product. So whereas SEM software concentrates on all the existing data sources, NFAT software focuses primarily on collecting and examining and analyzing all network traffic. It also provides a bunch of other additional features that you could research on your own. Now that we know the different sources of data that we're looking for, not all data is created equal, so I do want to touch on the value of our data sources, starting with IDS software. IDS data is important because it's often the starting point for examining suspicious activity. Not only do IDSs typically attempt to identify malicious network traffic at all the TCP/IP layers, but they also log many data fields and sometimes raw packets that can be useful in validating events and correlating them with data sources. SEM software ideally can be extremely useful for forensics because it's automatically correlating events among several different data sources and then extracts the relevant information and presents it to the user. The NFAT software is designed specifically to aid network traffic analysis, so it's always going to be valuable if it has monitored an event of interest. Firewalls, routers, proxy servers, remote access servers, by itself, these data sources usually have little data. Analyzing data over a large period of time can indicate overall trends, such as an increase in block connection attempts, etc. However, because these sources are typically record little information about each event, the data provides little insight as to the nature of the event itself. The DHCP servers typically can be configured to log each IP address assignment to the associated MAC address along with the timestamp. That's really helpful for analysts in identifying which host performed an activity using a particular IP address. Packet sniffers of all the network data traffic sources, this collects the most information on network activity. The downside, however, is the huge value of irrelevant data as well, millions or billions of packets, and typically provide no indication as to which packet might actually contain the malicious activity. Network monitoring software is helpful in identifying significant deviations from normal traffic flows, such as those caused by distributed denial of service attacks, during which hundreds or thousands of systems launch simultaneous attacks against a particular host or networks. And then the Internet Service Provider records. This information is primarily of value in tracing an attack back to its source, particularly when the attack uses spoofed IP addresses. The last thing I want to talk about in terms of getting data from the network is possibly identifying who the attacker was. Now, when analyzing most attacks, identifying the attacker is not an immediate primary concern. Ensuring that the attack is stopped and recovering system data are always the main interests. But things that can be done, contacting the IP address owner, can sometimes help identify who's responsible for an IP address. Usually that takes some type of escalation process. Seeking out assistance from the internet service provider, which does require a court order. It is only really done in the most serious attacks. Something that might be instinctual is when you have an IP address to try and ping it or send data that way. Really, this is not recommended for organizations. You could also look at the history of the IP address to look for trends and suspicious activity. And last, data packets could contain information about the attacker's identity. But again, our main goal is ensuring the attack is stopped and recovering system data are always going to be our main interests. We'll see you in the next video.